loop transfer function, which includes basically, it has two parts. One is used to investigate the servo performance, and the second part is used to investigate the regulatory performance. So these are the two equations, corresponding equations. First one is for set point tracking or servo performance. Second one is disturbance rejection or regulatory performance. Okay, this first one is also used for set point tracking performance, that is servo problem. Second one is also, for second one we also use the term disturbance rejection performance, that is basically the regulatory problem. Now to understand this, let us take one simple example. To understand how to develop the block diagram, let us consider one example. This is a liquid level system, which we have discussed several times before. You draw this schematic configuration. Okay, now if you recall the closed loop transfer function, that requires basically 5 individual transfer functions. One is GP, another one is GD. Both are specific to the process. Third transfer function is related to the transfer function of the controller. Fourth one is for measuring device, and fifth one is for final control element. I repeat, if we want to use the closed loop transfer function, then first we need to know the 5 individual transfer functions. What are those? GP, GD, both are specific to the process. GC, which one is specific to the controller. Fourth one is GM, that is specific to the sensor or measuring device. And fifth one is GF, that is the transfer function specific to the final control element. Now in this example system, we will discuss how we can have these individual 5 transfer functions. Okay, for this example system, we'll know how to get 5 individual transfer functions. So let us start from the process first. If we want to develop the transfer function for the process, first we need the process model. And that is why we have discussed extensively the process modeling part before. Okay, so this is a user process model. This modeling equation we have developed before, and transfer function, you know, it is in Laplace domain. That's why we need to take Laplace transform in both sides of this model. Transfer function is basically developed in Laplace domain, Accordingly, we are taking Laplace transform in both sides of the process model. We can rearrange in this form. And then we get equation 9. By this way, we get equation 9. And equation 1 I have shown before. Equation 1 is shown before. Okay. Now you see here manipulated variable f naught. That means m is f naught. And load variable we denote by d. So our d is fi. I repeat, manipulated variable we denote by m. So m equal to f naught. And load variable we represent by d. So here our d equal to fi. So that's why we have written like this way. You see, m is f naught and d is fi. Now if we compare equation 9 and 1, we get these two transfer functions gp and gd for the example process. Comparing equation 9 and equation 1, we get the transfer functions gp and gd for the example system. Okay, now come to the measuring device. For the measuring device, you first note down what is written in the right hand side. First, you note down what is written in the right hand side, or you can understand that part. See, we are using here basically differential pressure cell. So that is nothing but differential pressure transducer. And it works with this mechanism. Fine. Here P2 is basically the atmospheric temperature, atmospheric pressure. And P1 is this. So del P is this. In the differential pressure transducer, pressure differential is the input and output is the liquid height. So this is the mechanism used in differential pressure cell. Here you see H2 minus H1, that is H. We are considering here H1 is 0 and H2 is H. That's why H2 minus H1 rho g is basically H rho g. So from this equation we can write del P is proportional to H. What is written here you see? Del P is proportional to H. And thus del P equal to alpha H. Fine. Now you come to this left hand side. Measuring device, differential pressure cell. So for this differential pressure cell, we have second order dynamics. For this differential pressure cell, we have second order dynamics. In fact, this will, I hope, be discussed in the instrumentation part. Measuring device will be discussed in the instrumentation part. Okay. So here our input is HM, output is HM and input is H for the differential pressure cell. For a differential pressure cell, liquid height, original height, that is the input. And HM, which we are getting through measurement, that is the output for the differential pressure cell. And this is the internal mechanism of DP cell. Now, if we have this equation, second order differential equation, and if we take the Laplace transform in both sides, we get this transfer function. Kp alpha divided by tau square a square plus 2 zeta tau s plus 1. Fine. This is a transfer function for the measuring device. Now let us come to the controller part. For the controller, our comparator is HSP minus HM. It basically compares the set point and the measured height. And if we use PI controller, this is the transfer function for the PI controller. If you use PID, accordingly you can write here the PID controller transfer function. Okay. Roll number 10053, Soham Ujjal. Are you there? 10053, Soham. 57, Suresh Meena. 10057, Suresh Meena. Subhada Rishi, 10058. Are you there? Subhada, 10058. 59, Sarup Ranjan Mandal. 10059, Sarup. Okay. So this is about the controller part. Next, come to the final control element. Here our final control element is valve, is simply a control valve. And suppose it has the first order dynamics. So accordingly, we can write this expression, this transfer function for the final control element. So what we have discussed so far, among them, the final control element and the measuring device, they are under the instrumentation part. I hope they will be discussed in the instrumentation part. I repeat, measuring device and final control element, they are the part of the instrumentation. Okay, so anyway, so we have then total 5 transfer functions. 5 individual transfer functions we have discussed. Now we can develop the block diagram accordingly. We have discussed the 5 individual transfer functions. Now we can develop the block diagram accordingly. You see, this is the block diagram. If you want, you can draw this block diagram. First, we got the process. I'm a transfer function for the process. You see GP and GD. Okay. Then we have discussed controller. Then this is the measuring device. And this is final control element. Suraj Krishore, 30031. Are you there, Suraj Kishore? 30032. Karvi Jain. Roll number 30032. 30033. Aman Kedia. 30033. 3AP07. 19CH3AP07. 3PE01 Padmasri. Roll number 3PE01 Padmasri. 10074 Gaurav Jha. Are you there, Gaurav? 10074. Okay. So I hope you understood all. Now, what we will discuss next, basically we have developed the three control schemes: proportional controller, PI controller, and PID controller. And there are basically three control actions: proportional action, integral action, and derivative action. Now we want to discuss what is or what are the effects of this individual control action. I repeat, we have developed the control schemes by incorporating different ways the three control actions, namely proportional action, integral action, derivative action. Now we want to discuss the effects of these individual control actions one by one. What are the effects of proportional action? That we want to discuss first. What are the effects of integral action? That we want to discuss next. And finally, what are the effects of derivative action? Okay, that we want to discuss individually. Let us come first to discuss what is the effect of proportional action. Let us first discuss what is the effect of proportional action. So these are the steps we will follow. In step 1, we need to define all transfer functions. As I told, there are 5 individual transfer functions: GC, GP, GF, GM, and GD, that you need to either derive or you have to obtain if they are not given. So this is step 1. In step 2, you use the closed loop transfer function, equation 6. If you know all 5 individual transfer functions in step 1, we can easily write the closed loop transfer function by the use of equation 6. And based on this equation 6, we will go to analyze the closed loop behavior. In step 1, you try to obtain or get or develop the 5 individual transfer functions. Then in step 2, we'll substitute those individual transfer functions in standard closed loop transfer function represented by equation 6. And in step 3, we'll analyze different behaviors based on equation 6. So this is the common way or common procedure to analyze the closed loop behavior for the 3 control actions. Okay. Now, let us first consider the process. First, consider the process. So process may be first order, maybe second order, maybe higher order. Let us start with the first order process. Okay. In the first order process, this is the standard transfer function. I mean, this is the standard model. This is the standard model for a first order process. So what is KD, student? What is KD? In the right hand side it is written. Anyone? KP we know. What is KD? Anyone can tell? Adrija?
Yes, sir.
What
No,
is
sir.
KD? What is KP?
Sir, I forgot.
KP is a process gain with reference to manipulated variable.
Okay. So then
Can
K
you?
must be the
Yes,
gain with reference to the disturbance variable.
yes, correct. So KD here is the static gain with reference to disturbance. I think you can understand this transfer function easily. Fine. So earlier we did not consider this disturbance part. Now we are considering this disturbance part, and this is a equation. Now you know we have these two individual transfer functions for the process. One is GP, another one is ZD. Okay. As I shown, we are basically trying to have 5 individual transfer functions. Then only we can use a standard closed loop transfer function equation 6. So GPGD we got for the process. These are the two transfer functions we got for first order process, in fact. Then for measuring device and final control element, let us consider both of them as one. We are just assuming this for simplicity. GM and GF we are getting 1, and these two we are considering 1 just for simplicity. Since we are trying to investigate the effect of proportional action, so our controller is basically proportional controller. Okay, we are trying to investigate the effect of proportional action. That means our controller is only proportional controller. So our step 1 is finished. We know all 5 individual transfer functions. You see, GP we know, GD we know, GM, GF, GC, all 5 we know. So this is step 1. In the next step 2, we want to use equation 6, closed loop transfer function. Basically, we want to substitute these 5 individual transfer functions in the standard equation. If you substitute these individual transfer functions in equation 6, you will get equation 9. If you substitute all these individual transfer functions, you'll get this equation. And if we further rearrange this, we get equation 10. You let me know the expression for Kp prime and tau p prime quickly. Let me know the expression for Kp prime, tau p prime and Kd prime. Can anyone tell me what is the expression for Kp prime? We just
KPKC by 1 plus KPKC.
Yes, correct. What's your roll number?
30036.
What about tau p prime?
It will be tau p by 1 plus KPKC.
And then Kd prime?
KD by 1 plus KPKC.
Yes. So these are the expressions we get by comparing the last two equations. Okay. These are the expressions we get by comparing the last two equations. So here K prime means the closed loop static gains and tau p prime is basically the closed loop time constant. So, we have started with the first order process. Then we have added proportional action. Then we get the closed loop process. So what do you think? Is there any change of order? I repeat my question. We have taken a first order open loop process. Then we have added one P only controller. Then we get closed loop process in terms of equation 10. Is there any change of order? Tell anyone?
No, sir.
No. You see equation 10, it is also first order process, no? So there is no change of order. This is our first remark. We have taken a first order open loop process. We have employed one P controller and we get closed loop process, which is represented by equation 10. And there is no change of order, you see. So what do you think? Which one is larger, tau p or tau p prime? If you see this expression, or based on this expression, can you tell which one is greater? Tau p. Tau p is greater?
Yes, sir.
When? There must be some condition in terms of KPKC, no?
When KP and KC both are positive.
Yes. If KPKC is positive, then only we can say tau p is greater than tau p prime. So what is the meaning of this? What is the physical significance? If we employ the controller, our tau p value gets reduced. What is the physical meaning of this? What is the physical significance of this?
The closed loop response is faster.
For which case?
For tau p greater than tau p bar.
Yeah, I'm asking that which one is faster, open loop or closed loop?
It's a closed loop.
Yes, correct. What's your roll number?
It's a 30019.
So we can write this. You see, closed loop response is faster than open loop response. Correct. But I have written one statement, you know, KPKC is always positive. Why? So you try to find the answer. Why KPKC is positive? This is your task. You try to find the answer. If not, you tell me, I will discuss. So similarly, what do you think? Which one is greater, KP or KP prime? You just see this expression. Based on this expression, can you tell me which one is greater, KP or KP prime? Anyone? Based on this expression, can you tell which one is greater, KP or KP prime? Student, anyone can tell? Okay, I'm giving one hint. KP and KC, they are same in sign. If KP is negative, KC is also negative. If KP is positive, KC also positive. Now can you tell? KP and KC both are same in sign. In that case, which one is greater, KP or KP prime?
KP prime.
KP prime is greater.
KP is greater.
KP is
KP is
greater.
greater.
You see? KP is greater. What is the physical significance again? Anyway, before that, we can write straightforward way. KD is greater than KD prime because this expression is similar with the tau p expression, you see. So what is the physical significance? Gain is getting reduced in case of closed loop process than the gain of open loop process. What is the physical significance?
The static gain is always less.
Yes. What's your number?
It's a 19CH 30019.
Correct. The steady state gain Sasank Gautam, no? Okay.
Yes, sir.
So steady state gain gets reduced because this is related to the gain. In fact, related to this, I'll show you the graphical representation. So again, this is the second question. I have written KP and KC, they are same in sign. Now this is second question, you have to find the answer. If you do not get, let me know. I will give the answer of these two questions. First one is KPKC is always positive, and second one KP and KC, they are same in sign. These are the two questions given to you. You try to find the answer. Okay. Now we got the closed loop transfer function, you know. Based on that, now we want to investigate individually for servo case and regulatory case. Okay, so we got this equation 10. Now we want to investigate, or we want to extract different features of this closed loop process by individually analyzing the servo and regulatory cases. Let us first consider the servo case. So this equation 10 we got previously. Now for servo case, I have mentioned that the disturbance term is 0. That means the second term gets omitted. I mean, we are not considering the second term. So this is our closed loop transfer function for the servo case. We have just considered the first term. Okay. Let us introduce a step change in set point. A step change in set point with magnitude capital A. Let us consider a step change in set point with magnitude capital A. Now, if we take the inverse of Laplace transform, we get equation 11. If we take the inverse of Laplace transform, we get equation 11. So equation 11 is the dynamic equation of the closed loop process for servo case. Equation 11 is the dynamic model because y is varying with time t. That's why it is dynamic model. And this equation 11 is obtained for step change in set point and for servo case. Now, what is the graphical representation of this? This is the graphical representation, you know. This is the graphical representation. You just draw this figure first. So initially this is our set point value. It is, you can say, 0. Then at a particular time instant, we are introducing a step change in YSP, which is shown through the red color. And this magnitude is capital A. This magnitude is basically capital A. Okay. Now, if we simulate or solve this equation 11, we get this type of response with time. Fine. If we just solve equation 1 and if we plot, it looks like this. This one. Okay, it is first order response. You just recall, it is a first order response. So this is a Y profile. So obviously after a certain period of time, Y becomes constant, you see. So that's why it is called steady state error. And I have written here some term for offset. We want to find out whether this is correct or not. I have shown this is the offset. Now question is how to calculate this offset, that we want to discuss next. I have written one expression for offset. The question is how to calculate this offset or steady state error. This is the formula for offset. Offset equal to new set point minus ultimate value of the response. Ultimate value of the response we can get from final value theorem. You note down the expression or formula in fact we use to calculate offset. It is basically new set point minus ultimate value of the response. As shown here, ultimate value of the response, in fact we discussed this also, we calculate by the application of final value theorem. So accordingly what we get? You see, accordingly we get this. Our new set point is A, and if we apply the final value theorem in Laplace domain, we have this expression. Is this matching, student, with your result? Offset? Anyone can respond?
Yes.
Okay. So you see, I have shown for the case of servo problem, okay, how we can get the dynamic equation in terms of y against a step change in set point. So similarly, in the next phase, we will discuss how to get the dynamic equation in case of regulatory problem. In the similar fashion, there we will consider a step change in D. Okay, so this is basically the offset calculation in case of servo problem. Next, we will consider in a similar fashion how to find the dynamic response for regulatory problem and what is the offset. Let us start with equation 10 with YSP equal to 0. Then you see we get this equation. Now, as I told, in the similar way, we will consider a step change in disturbance with magnitude A. We are considering a step change in disturbance with magnitude A. Now let us take the inverse of Laplace transform in both sides and get equation 12. Fine. Can you find the offset now, student, for this case, regulatory case? Find it and let me know how much is the or what is the expression for offset. I have shown the derivation till equation 12. Now it is your task to find the expression for offset. Do it. I have shown in fact for the servo case.
Sir, it is A times 1 plus kpkc minus kd whole divided by 1 plus kpkc.
No, it's not correct. And I'm assuming that, in fact, I'm expecting that you'll do the mistake. See, you can consider this as an alarm. I am somewhat, sure that you are going to do the mistake. So I will be very happy if someone tells me the correct answer. Anyone else get any other expression?
Sir, A into KD minus 1 minus KPKC upon 1 plus KPKC.
No, still it is not correct. See, anyone got this answer? You see, I am showing you. See the offset. In fact, you draw this figure as well. Anyone got this expression?
Like we will again consider the ultimate value of response.
You did not consider?
No, like if we do like the t is infinity, then we will get this value.
Sir, we will get this if the new set point is taken 0.
Correct. What's your roll number?
19CH 30008.
Can we consider it? He is suggesting that we can get this offset if our new set point is considered as 0. My question is, can we consider it? So what you have considered at the beginning, y set point?
Yes, sir,
Here?
because we have considered the regulatory problem. So
Yes. So as I mentioned that it is quite expected that students are usually doing the mistake first time. So you remember this. Okay. So for regulatory problem, set point is 0. So that's why our new set point is considered here 0. Did you draw this figure? Then I can move forward. You see, this is a value. I think you know all now. For the regulatory case, new set point is basically 0. For the ultimate value of the response, you simply apply the final value theorem and get the offset. Now here I want to give another explanation. Can you recall I have shown Kp is greater than Kp prime. Kd is greater than Kd prime. That means gain of the closed loop system gets reduced. So this is the physical explanation, you see. Here gain is reduced. That means this offset is lower than this deviation when there is no controller. I repeat, just a couple of minutes back, I have shown Kp is greater than Kp prime and Kd is greater than Kd prime. What is the physical significance that we can have from this plot? No control means Kp and Kd. With control means Kp prime, Kd prime. And you are understanding the deviation is less for Kp prime, Kd prime. And deviation is more for Kp and Kd. This is the physical explanation we can have from this. Okay. Now you see offset tends to 0 when Kc tends to infinity. So in both the servo and regulatory case, this comment I made. When Kc is very, very large, our offset tends to 0. Now, naturally, one question arises, can we take very, very large Kc value? Do you have any answer, student? I have shown for both the servo and regulatory cases, if Kc is very, very large, our offset is very close to 0. Now, question is, can we take then very large Kc value? Is it possible? Answer is no. The reason is given here, you see. The maximum allowable value for Kc is K suffix U. That is called ultimate gain. I will show you this, what is ultimate gain. Okay. But for the timing, you just remember this. Maximum value of Kc allowed is ultimate gain. That is K suffix U. If you go larger than that, we can have instability problem. If you recall the plots I have shown also, no, if we increase the Kc value, we get more oscillatory response. So if Kc increases, the oscillation, amplitude of that wave gets increased. So by that way, we can have some instability problem. So that's why we cannot take very, very large Kc value.
So can we say that we can't take large Kc value because then P only controller behaves like an on-off controller?
Yeah, that is also another point. That is also another point. Yes, that is true. Okay, and this part, this ultimate gain, what is the limit for Kc value, we will discuss later. That's what I have written here. And the second point you just note down. We have considered Gf, Gm, that they are equal to 1 for simplicity, but we can go ahead with these two also. Gm equal to Km and Gf equal to Kf. In that case, these are the expressions for offset. Yeah, I think you take 5 minutes break and then we'll again come back. Okay, let us start again. So I hope all of you understood till this point. In the next phase, we'll take one example. Okay, let us take one example. And for this example system, our target is basically to find offset. I repeat, we are going to discuss with an example that is a pure integrated system. And our goal is to find the offset for this process. So we'll follow the 3 steps procedure I have shown before. In the first step, we will try to know the 5 individual transfer functions. In the second step, we will write the closed loop transfer function equation. And in the third step, we will analyze the dynamics that includes offset as well. Okay. Now here our control objective is to maintain this height at its desired level, that is set point. That's why our control variable is also height. And among these two inputs, we are considering one as manipulated variable and another one as load variable. So this is the model equation. So you are understanding that here this model is directly written in deviation variable, although I did not use prime symbol. This model equation is written in terms of deviation variable, although we did not use here prime over the variables. Now let us take Laplace transform and get the transfer functions for the process. We have started with the process. For that, model is written in terms of deviation variables. Next, we take the Laplace transform and then we get transfer function for the process, GP and GT. Okay. Now let us come to the controller. Controller, you know, P only controller. I mean, we are considering only the proportional action. So naturally our controller is P only controller. And for sensor and final control element, we are still considering one just for simplicity. For sensor and final control element, we are considering their transfer function as one just for simplicity. Now you go to the second step. You find the closed loop transfer function by using equation 6. Proceed. Find the closed loop transfer function equation using equation 6. Student, you proceed. All 5 individual transfer functions are known to us. Now you use in the second step equation 6 and find the closed loop transfer function expression. You can match now. If you got this or if you agree with this equation, you just go to find the offset for servo problem. If you understood till this point, you go to find the offset for servo and regulatory problem separately. If anyone got the offset for servo problem, let me know. Anyone got offset for servo problem?
Sir, is it 0?
Yes, correct. What's your number?
19CH30034.
Yes, it is 0. Go for regulatory case.
Sir, minus A.
For regulatory case,
Minus A.
minus A. That means you have considered A by S, step change in disturbance.
Yes, sir.
No, still not coming. Just recheck.
Okay, sir.
Anyone got offset for regulatory case?
So minus 1 by Kc.
Yes, correct. What's your number?
So 19CH30019.
Minus 1 by Kc, you see. So, even with the use of P only controller for this liquid level system, we got offset equal to 0 for servo case. So this is an exceptional case. Okay. Usually with P only controller, we have offset. But for this particular example, we got offset equal to 0 for servo case. So this process itself has some integral action. Okay, and this is considered as an exceptional case. So you can note down these points. So usually the liquid level, I mean, that much accuracy is not needed for maintaining the liquid level. If that is the case, we can go ahead with this P only controller for liquid level control. For servo case, we perfectly got offset equal to 0. For regulatory case, we got -1 by Kc. So if there are two options, we can consider a little higher Kc if possible. If not, liquid level, if we do not need to maintain so accurately, then we can go ahead with this P only controller. Okay, and this is definitely an exceptional case. Now, so far we have discussed, in fact, we have determined the offset for a first order process. Now we want to consider a second order process and we want to see what is happening in terms of offset. I repeat, so far we have considered a first order process. In the next phase, we want to consider a second order process. And we want to see what is happening with second order process plus P only controller. What is the offset? That we want to just go through once briefly. Yeah, you have any questions, student, till this point? If not, we'll go to the next topic. If you have any question, you can ask me now. Okay, good. So let us come to the second order process. And here we will only consider the servo case. We'll repeat the same procedure for the second order process. And in fact, here we are considering only the servo case. We are again considering GF, GM. They both are equal to 1. And that is just for simplicity. Now we have all four transfer functions. You see, GD we don't need for the servo case. We have the information of all four transfer functions. And then we can move to the second step. That is the derivation of closed loop transfer function. So this is the closed loop transfer function for the servo case. This is a standard equation. And we are simply substituting all individual transfer functions therein. This is the standard closed loop transfer function for servo case. And here we are just inserting, plugging in all individual transfer function. And finally, we get this expression. Can you tell me the expression for Kp prime, tau prime and zeta prime? Let me know the expression for Kp prime, tau prime and zeta prime.
Sir, Kp prime will be Kpkc upon 1 plus Kpkc.
Tau
And
prime. Yeah, tau prime.
Tau prime is tau upon 1 plus Kpkc.
No, one root is there. What's your roll number?
19CH 30008.
Yeah, you check the tau prime expression. And zeta prime also I want to know. Anyone
Sir,
else got?
is
Yes.
tau upon under root 1 plus kpkc.
Tau?
Tau by 1 plus under root 1 plus kpkc.
Yeah. And zeta prime?
Sir, it is zeta by under root 1. No, it is zeta by under root 1 plus kpkc.
What's your roll number?
19CH 10007.
Yes. All of you got this? Abbas Sarkar? Abbas, are you there?
Yes, sir.
You got these expressions? Or trying?
Still trying.
So comments are same, you know. Kp is greater than Kp prime. And second order process plus P only equal to second order process. There is no change of order, you see. We have started with second order process and we end with second order process. So our first remark, there is no change of order. You note down this. We have started with second order open loop process. We have ended with second order closed loop process under P only controller. So there is no change of order. This is first point. Second point, as usual, Kp is greater than Kp prime. Tau is greater than tau prime. Zeta is greater than zeta prime. And you try to find physical significance. I have told for first order process. Now you find what is the physical significance of this. Second remark is quite clear. That is same with the first remark of the first order system. Only you need to find the physical explanation, or you will have the physical explanation for third remark. Can you find the offset now for the second order process and for this servo case only? Let me know the offset. What is the offset for this process? You may consider unit step change instead of A by S. You can consider 1 by S. Anyway, whatever may be. You can consider YSP equal to 1 by S.
So minus Kp prime.
Minus Kp prime. Why?
So,
What about?
We will use the final value then where limit is tending to 0 s into
Sir, 1 minus Kp prime.
Yes. What's your number?
19CH 30008.
Yes. Anyone else got?
Yes, sir. 1 minus Kp prime.
Yes. I think the first who told it is minus Kp prime, he did not consider perhaps this new set point value. Agree, student?
yes sir.
Yeah, you consider because this is servo case, no? And the same comment, if Kc tends to infinity, this offset tends to 0. Okay, but as I mentioned, Kc must be lower than the ultimate gain. So ultimate gain is not so high value. And Kc is very, very large value, then only it is on off control. But in many cases, at very, very large Kc value, we may have instability problem. Now you see what are the effects of increasing Kc. These are the effects. Speed of response increases. Speed of response, it means that it is reaching faster. I mean, it's reaching this ultimate value earlier than the other cases. You see, Kc1 is the largest value. So that's the speed. It is reaching first time the ultimate value earlier than the other cases. Offset is obviously getting reduced. From the expression we can comment this. And second one, you see disadvantage, overshoot increases and longer oscillatory response. In fact, it is not shown this last point, longer oscillatory response. You can do one thing, from here you make the horizontal line. Student, you follow this, what I'm saying. Longer oscillatory response, that is not very clearly reflected here. So you do one thing, from this peak, you draw a straight line. Draw a horizontal line. It means that the green color reaches steady state before this black color. Fine. From here you draw the horizontal line. From here, horizontal line, offset. It means it reaches the steady state faster than that of the black one. Okay, from here you draw the horizontal line. So this is all about, our proportional action. The effects of proportional action. Particularly, we have seen the speed of response, we have seen the offset. These are the two major issues, and definitely for them we have derived the dynamic equation. Now, in the similar fashion, we want to investigate the effect of integral action in the next phase. I repeat, This is all about the effects of proportional action. We have discussed the offset, we have discussed about the gain Kp, Kp prime, we have discussed about the time constant tau p prime for first order case. All these are discussed today itself. Now further we want to extend this study to investigate the effect of integral action. Let us come to that topic, effect of integral action. And for this we are limiting our study only for the servo case, because for regulatory case you can easily extend the study what we are going to conduct. Okay, we have discussed both servo and regulatory case for proportional action. Now we are just going to consider only the servo case to investigate the effect of integral action. So accordingly, this is our closed loop transfer function. This is a standard form. In fact, this we can get from equation 6. Let us consider a first order process. Can you tell me now what should be the controller transfer function, student? What is the controller transfer function for this case? Anyone? If we consider only the integral action, what is the controller equation, student? Anyone can give the response?
Sir, Kc by tau s.
Kc by tau is correct. Roll number 8.
19CH30029.
Correct. So this is our controller equation. You see, we are just picking up only the integral action. We are not considering proportional, or we are not considering derivative action. And as usual, our sensor and final control element that we are getting, that we are considering 1. Okay, we are considering first order process. Our controller is integral controller. And for simplicity, we are considering sensor and final control element, transfer function equal to 1. So accordingly, we get this closed loop transfer function equation. Let me know the expression for tau and zeta. Just compare these two terms and let me know the expression for tau and zeta. Anyone got the expression? For tau and zeta?
So tau is under root tau y tau p.
Only. Something else is there. You just recheck.
So tau is under root tau I tau p upon kpkc.
Yes. What's the roll number?
19ch 30008.
Correct. And what about zeta?
Sir, it is tau root over tau I by 4 tau p kp kc.
Correct. What's your roll number?
So 19ch 30019.
You can match with these expressions. Got? So you see, we have started with the first order open loop process, and we have ended with second order closed loop process. So obviously order is increased by 1. Let us come to the remarks. Our first remark is, we have started with first order open loop process, and we have ended with second order closed loop process. So order is increased by 1. So what is the physical significance? Increasing order means what happens? If order increases, what happens? You can give the answer also from a plot I have shown, comparing response of first order, second order non-interacting, second order interacting, fourth order
Response
non-interacting.
becomes sluggish.
Yes. Three triple zero eight. What's your number? 30008?
Yes, sir. Yes,
Yeah.
sir.
So you see, this is our first remark. As I told, we have started with first order open loop process. We have employed integral action. And finally, we got second order closed loop process. So integral action makes the closed loop response sluggish. This is a drawback, you remember. Although when I will conclude all these actions, I'll draw all these remarks again. Okay. Second one, you come to this equation. And I think you can understand this point. Here jitter direct, I mean, depending on Kc and tau I, which are controller tuning parameters. But you know, whenever you are considering a process for control, that Kp and tau p values for that particular process is fixed. So that's why we are not going to draw any conclusion on this. I mean, we are not going to vary, we are not going to change Kp or tau p. We cannot change them. Okay, so that's why I have written Kp and tau p, they are fixed for a particular process for which we are going to study the control closed loop response. We can vary Kc and tau I because these are tuning parameters. So ultimately we have to fix the best Kc and tau I values. Better to say optimal Kc and tau I values. Now you're understanding this closed loop response basically depends on the tuning parameter values. Closed loop response means it may be overdamped, it may be underdamped, it may be critically damped. And you know their limit in terms of zeta. Okay. You know their limit for zeta, like zeta greater than 1, it is overdamped. Equal to 1, critically damped, like less than 1. So basically this overdamped, underdamped, critically damped, they depend on the Kc and tau I values. Okay, it is quite obvious from equation 13b. Now from again equation 13b, we can see that if Kc increases, zeta decreases because Kc is present in the denominator. If Kc increases, zeta decreases, which is obvious from equation 13b. It means if you have initially overdamped response and you are going to increase Kc further, you may get oscillatory underdamped response. I repeat, initially suppose your closed loop process is showing overdamped response and you are going to increase the Kc value further so that zeta gets reduced and it is in between 0 and 1. In that case, we will have faster oscillatory underdamped response. Not only that, overshoot and decay ratio, they both also increase with increasing Kc. So if we increase the Kc value further, zeta may come into the bracket, I mean in between 0 and 1. In that case, we may have oscillatory underdamped response and which results in increased overshoot and decay ratio. So what is the overall? Speed of closed loop response gets improved at the expense of higher deviation and longer oscillations. Speed of closed loop response gets improved at the expense of higher deviations and longer oscillations. Speed of closed loop response gets improved at the expense of higher deviations and longer oscillations. So this is this overall comment we have if we increase the Kc value. And let me show this graphically. This is the graphical representation. So this is only for integral controller, you remember. This is only for integral controller. So if we increase the Kc value, it is very clear we are having faster response. So speed of response gets improved. But you see, we are having higher deviations and longer oscillations with the increase of Kc. But definitely there is no offset. As I have shown previously for P-only controller, there is certain offset, but under integral controller, there is no offset. In fact, we will prove this a little later. There is no offset under P-only control integral action. So this red dot line basically denotes the set point. Okay, this red dot line this denotes the set point YSP. Now let us come to the fourth point, where we are considering the decrease of tau I. Zeta decreases because tau I is present in the numerator in equation 13b. So it is just reverse, okay, because tau I is present in the numerator, whereas Kc was present in the denominator. And I have shown again there is no offset. In fact, for integral action, I have shown before also that it eliminates the offset. So same observations as in last remark 3. But only thing here is that we are going to decrease tau I value. In remark 3, we have increased Kc value. Can you find now offset? You just use your closed loop transfer function equation you have derived. In the fifth point, we want to find the offset. So for this, you just consider the closed loop transfer function you have derived before. See, this is your closed loop transfer function, this one. You just consider this one for finding offset. I repeat, this is a closed loop transfer function we have derived, and we want to use this equation for finding the offset. Let me know now what is the offset.
So 0.
Got offset?
This is 0.
0. Yeah. What's your number?
19CH10061.
Tridipta. Yes. Anyone else got the value? J 30008 got the value for offset.
Yes, sir.
How much?
0.
Yes. So in fact, I have shown for Sarbo case, but even if you can go with regulatory case as well, it is always 0. Offset is always 0. So that's why I told you cannot write integral action reduces offset. It perfectly eliminates offset. So you remember, if somewhere you were showing with your simulation, there is a little offset, you cannot justify it. You have to show zero offset. If not, your tuning parameter values Kc and tau y, they are not correct. Okay, I'm talking about the overall. Suppose you are taking a very large process, maybe distillation column, and you are employing one PI controller or integral controller, and you are showing that there is a very little offset, but you cannot justify. You have to show perfectly zero offset. So, okay, this is all about today. Now, if you have any doubt, you can ask me. Any doubt, student? Siddhant is there, 30023. 30023, Siddhant. Are you there? Okay, no problem. Any doubt, student? No. Okay,
Sir,
then.
I couldn't understand.
Yes, tell.
Sir, I couldn't understand the part in which you said that the longer oscillating response in the effects of increasing Kc.
Here you were saying?
Um, sir,
For
in the
which
P only
controller?
action. In P
P only
only
action.
effects of P.
Oh, I told some correction, that you were saying?
Yeah, like what does it mean?
Basically, you see, here oscillation is for a longer time. Okay. If you have very large Kc value, then you will reach first time the ultimate value faster, earlier than the other plots. So it has reached the ultimate value first time. You see what we call, rise time. Rise time is less. Secondly, it will oscillate for a longer time. But from this plot, I have shown both the black and green lines, they are oscillating to the same time instant, to the same time period, but it's not like that. For Kc1, it will oscillate for a longer time. For green color, it will oscillate for a shorter time. So that is why I told you just make the horizontal line from here so that it reaches set point before than that of this black color. I repeat, it will oscillate for a longer time and green color will oscillate for a shorter time. That means this green color will reach the steady state earlier than this black one that you saw through this plot. Got it?
Yes.
Yeah, that's why I told you just make one horizontal line from here itself. From here. That means it reaches the steady state faster than the black one. Any other question? Okay then, thank you.
Thank you, sir.
Thank you to everyone.